So in this video, I'm going to be solving the June 2024 question 6 at A and B. So the question reads, a low voltage lighting system is to use a binary logic control for a particular light. The light lies at the intersection of a T-shaped hallway. Okay, so I have a T-shaped hallway. So the light is here at the center. Light L. Okay. So there are switches, so there's switches X1, X2, and X3. Okay. The switches of binary output 0 and 1 depending on the position and names are X1, X2, and X3. The light is controlled by an amplifier driving a thyristor. So it says when Z, the input to the amplifier is 1, the light is on, and when Z is 0, so when Z is 1, we have on, and Z is 0, we have off. Okay, like this. So the function that so X1 and X2 and X3 are fed as inputs to give a result to the Z output, so that if any one of the switches is changed, the value of Z changes, turning the light on or off. So the key fact is that the key takeaway point is that whenever any of these inputs are changed, that value must be changed. So we have an AND gate. Okay, an AND gate requires all the inputs to be on for it to give you a high. So we can't use an AND gate in that case, and an AND gate is the opposite. So and then we have an OR gate. An OR gate requires one input to be on. So in an OR gate, if you have, let's say you have a binary combination of 0, 0, 1, this light is going to be on, right? If you have 0, 1, 1, it's also going to be on. But in an OR gate, what will happen is that it does not change directly just on multiple inputs seem to have no effect, because only one can power it. The second one seems to make no change to the circuit. It still remains on as much as it is a high. But the gate that we can use that is going to help us to see that whenever any change is made, it's going to change. It's going to be an exclusive OR gate. Why an exclusive OR gate? Because an exclusive OR gate, it only requires one input to be on, and after that to be off. So if you have 0, 0, 1, the light will be on. If you have 0, 1, 1, the light will be off. And that means this BT would have changed. Okay, another gate that we can use is exclusive OR gate, because also the exclusive OR gate is going to help us. It's going to be switching bits immediately, just one change is made. Okay, so they're saying, what is the equation? Find the function that we need for this circuit. So the function is just going to be all the inputs combined, but just using what? Using an exclusive OR gate. Okay, so we're going to have X2 like this. We're going to have X3 like this. So in part A, that is going to be the function that we're going to use. Okay, then part B says part B. Okay, so maybe let me verify this through a truth table. So if I have a truth table of X1, X2, and X3 as inputs and Z as an output. So I'll say 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, like this. Okay. So if you see, this is 0, 0, 0. Let's say that this is firstly what? This is going to be off the first time. So the first time will be a first change here. This is going to be what? This is going to be 1. It's going to be on. Here we have this change, but this change we only have one bit that's active, so this is going to be on. And then in this change you have 2 bits, so there's a change, but this is going to be off. And in this change here it's going to be on because of one bit that's active. In this change we're going to have it's going to be off because we have 2 bits that are active. That's how an exclusive OR gate operates. And in this case, this is going to be off, this is going to be off. Okay, so this is how it's going to happen. So upon any change, whether you introduce a 1 or a 0, and depending on the arrangement of the bits that we have, we're going to have this operation. So this is going to be, that's going to be the truth table that we're going to have there. Okay,